Section 1.4, we examine velocity and acceleration in two dimensions. Sample problem number 1, calculating velocity using the component vectors. A family drives from St. John, New Brunswick to Moncton, assuming a straight highway. And I want to pause for a second and highlight that this is a straight highway. This will come into play when we look at part B. This part of the drive has a displacement of 135.7 kilometers, 32.1 degrees north of east. From Moncton, they drive to Amherst, Nova Scotia, and the second displacement is 51.9 kilometers, 25.9 degrees south of east. The total drive takes 2.5 hours to complete. Calculate the average velocity of the family's vehicle. I've drawn rough sketches of each of the individual displacements, delta D1 and delta D2. When answering this question using component vectors, the very first step is to break each vector into x and y components. I'm going to draw these x and y components. Delta D1x is the adjacent with respect to the hypotenuse and the angle, which represents the cosine trigonometric ratio. So this becomes 135.7 cos 32.1 degrees. The x component of delta D2 is again the adjacent with respect to the hypotenuse and the angle. So it would be 51.9 cos 25.9 degrees. Let's look at the y components. Delta D1y is the opposite with respect to the hypotenuse and the angle. Opposite hypotenuse is the sine ratio. So this would be 135.7 kilometers times the cos of 32.1. And the y component of the second, delta D2y, is 51.9 kilometers cos 25.9 degrees. In step 2, we're going to add up all the x components and all the y components. So we'll find the total, delta dx total, and delta dy total. Now I am going to use a sign convention. I'm going to let east and north be positive. So when I find the delta D x total, it will be equal to delta D1x plus delta D2x. Both of these are pointing east, so they'll both be positive. So it'll be plus 135.7 cos 32.1 degrees plus 51.9 cos 25.9 degrees. If we compute this into our calculator, we get a total of 161.6 kilometers east. Let's do the same for delta y total. Delta y1 is north, delta y2 is south. So this one will be positive and this one will be negative. So we have 135.7 cos 32.1 plus 50, I'm glad we paused here for a second so we can make special note that this vector is south, so I'm going to make it negative 51.9 kilometers sine 25.9 degrees. I just noticed that I made these all cos instead of sine. All right, when we punch these into our calculator, we end up with 49.4 kilometers north. In step 3, we're going to make a right angle triangle and find the total displacement. So we have 161 east plus 49.4 kilometers north, and our total displacement can be found using Pythagorean theorem. For the two sides. If we punch this into our calculator, we get 169.0 kilometers. To report the direction, we're going to use the opposite and the adjacent and the tan ratio to find theta. So theta is equal to the inverse tan of 49.4 over 161.6. If you punch this in, you end up with 17 degrees. So if I want to find my velocity, which is equal to total displacement over elapsed time, that would be 169.0 kilometers, 17 degrees north of east, divided by 2.5 hours. If we punch this into our calculator, we end up with 68 kilometers per hour, 17 degrees north of east. In part B, we want to find the average speed of the family's vehicle. speed is a scalar quantity, and we mentioned up above that this highway was a straight line. So I know that the distance traveled is equal to the magnitude of displacement 1 plus the magnitude of displacement 2 divided by the elapsed time. So we have, from the original displacements, 135.7 kilometers plus 51.9 kilometers divided by 2.5 hours, we end up with 75 kilometers per hour. We've talked a lot about adding vectors in 2 dimensions, but today we're going to spend some time talking about vector subtraction. And this is especially helpful when we are doing calculations with acceleration. As we remember, acceleration is equal to the change in velocity over time. And we know that the change in velocity is equal to v2 minus v1. So here we would be subtracting vector quantities. And there are 2 ways to do this. The first is by vector subtraction. And let's take a look at this example. In this example, we're going to find delta v, the change in velocity. We have the initial velocity in this direction and the final velocity in this direction. So, delta v is equal to v2 minus v1. We can also write this as v2 plus negative v1. So our v2 and our v1, let's draw them for a second. I'm going to draw them a little bit bigger so that we can see them. This is v1. And this is v2. If we look at this statement, in order to find delta v, we are going to add v2 plus negative v1. So we have positive v1. What would negative v1 look like? If this is positive v1, then negative v1 would simply look the same, just in the opposite direction. So I can add negative v1 and positive v1 tail to tip. And our answer would be the line that joins these two together, tail to tip. So our answer, delta v, would be this line here. Now there's a second way to do it, and that way is called tail to tail. Instead of taking the vectors and flipping their direction, we can simply place them tail to tail. So let's do this again. v1 and v2. We can take these two vectors and place them, instead of tail to tip, we can place them tail to tail. In order to find v2 minus v1, we will draw a line, and this is for tail to tail. Draw a line from initial to final, from v1 to v2. And this is our answer, delta v. So we can find change in velocity, where we're subtracting two vectors, by flipping one of the vectors' directions and adding them tail to tip. Or not switching them and adding them tail to tail. Both of these methods give you the same answer. Let's do a problem where we're calculating acceleration in 2 dimensions. We're going to look at this in 2 different ways. First, I want us to look at it in terms of component vectors. A car turns from a road into a parking lot and into an available parking spot. The car's initial velocity is 4 meters per second, 45 degrees north of east. The car's velocity just before the driver decreases his speed is 4.0 meters per second, 10 degrees north of east. The turn takes 3 seconds. Calculate the average acceleration. So if we're doing component vectors, let's follow the same steps we did above. We're going to break each vector up into x and y components. This is the adjacent with respect to the hypotenuse. So this will be 4.0 cos 45 degrees. The y component is the opposite with respect to the hypotenuse. So v1y will be the sine trig ratio, so 4.0 sine 45 degrees. We'll do the same for v2. v2x is the adjacent with respect to the hypotenuse and the angle. So again, we're looking at cos. 4.0 cos 10 degrees. And v2y is the opposite, therefore sine. 4.0 sine 10 degrees. So, our goal is to find the change in velocity. The first step we're going to do is find delta Vx, which is V2x minus V1x. So it's 4.0 cos 10 minus 4.0 cos 45 If you punch this into your calculator, you get 1.1 meters per second east. Let's do the same. Let's find delta V in the y direction. It's equal to delta V2y minus V1y. So V2y is 4 sine 10 degrees. And V1y is 4 sine 45 degrees. If we punch this into our calculator, we end up with negative 2.1 meters per second north, which is the same thing as positive 2.1 meters per second south. All right. So to find delta V, we're going to add these two component vectors and make a right angle triangle. So we have 1.1 meters per second east and 2.1 meters per second south. Delta V is the line that joins these two together. We can find the magnitude of delta V using Pythagorean theorem. If we compute this, we end up with 2.4 meters per second. To find the direction, we're going to use the opposite and the adjacent. This is the tan ratio. So theta equals inverse tan of 2.1 over 1.1. And we end up with 62 degrees. So we can find our acceleration, which is change in velocity divided by time. Our change in velocity is 2.4 meters per second, 62 degrees south of east, divided by an elapsed time of 3 seconds. If we punch this into our calculator, we get 0.80 meters per second squared, 62 degrees south of east. Now, we can take these two original vectors and we can find the change in velocity using a diagram. And we would do that by placing them tail to tail. And our answer would be the line that joins the initial to the final. If we did them with a scale diagram, this change in velocity is the same as we found using the component vectors. When it comes to a test, the choice is yours, which method you prefer. Now, I would like you to try the homework problems at the end of this section from your textbook.